Welcome to lesson 3.8. Today we're talking about all of those transformations combined together. So far we've talked about horizontal shifts, and vertical stretches and horizontal stretches. So what we're going to look at now is how horizontal and vertical stretches and compressions are related to each other. And then we're going to be talking about getting an equation from a graph. So that's part of your homework today. But for now, can you please graph both of these functions on this grid together? Pause the video and then unpause when you're ready and we'll go through them. So a couple things you should have noticed first is that they are both square root functions. And there's two things. As soon as we identify what the function family is, we want to know what the step pattern is, and we want to know what the key point is. And so for square root functions, the key point is 0, 0, like all of them. And then our parent step pattern means that we're going to count from our key point. We're going to go to the right and up certain things. That's our parent function. So if I go 1 to the right, well, the square root of 1 is 1. I'm going to go to the right 4. Well, the square root of 4 is 2. And I'm going to go to the right 9, and the square root of 9 is 3. These numbers are chosen because they are perfect square numbers. That's why we picked them, because they work perfectly. So if I'm going to graph this one first, just because there's less going on, we'll start here. There are two things that I notice are happening. One is that I've got this negative with our horizontal stretch or compression. And so if this negative is there, that means it's a reflection in the y-axis. It's a horizontal reflection. So that means if it's a horizontal change, we need to change the direction we're going horizontally. So now we're not going to count right, we're going to count left. So that's how we take this negative into account, this reflection in the y-axis. The other thing that we want to take into account is that 2. Okay? This is in the spot of a horizontal stretch or compression. And we know that because it's with the x in the function. So it's underneath the square root. If it was a vertical stretch or compression, it would be in front of the square root. It wouldn't be inside. The same is true for an absolute value function. It's got to be inside the absolute value signs to be the horizontal. If it's in front, then it's vertical. Same thing with parabolas. It's got to be inside of that square, in the brackets with the x. If it's outside of the square, in front, then that means it's a vertical stretch or compression. The same is true with all of them. If it's on the bottom of the fraction of an inverse function, then it's part of the horizontal change. If it's in front or outside of the fraction, then that means it's a vertical change. So keep track of which one is horizontal and which one is vertical. Now, we know that the horizontal stretch or compression, this is the k value. Well, the stretch or compression factor means we have to take the inverse. So it's not a stretch by 2, it's a compression by a half. We only have to do this to the horizontal stretch or compression. We don't change the vertical at all. So this means it's a horizontal compression by 1/2. We just take the reciprocal of the 2. So it's 2 over 1, we flip it, the compression is a half. How do we take that into account? Well, it's horizontal, so we need to look at the horizontal steps. So we're going to multiply all of these by our 1/2. Now I just need to plot my points. So in this equation, I didn't have a vertical shift, so there's nothing at the end to move it up or down. And there's nothing after the x inside of the square root that would shift it left or right. So my key point stays the same at 0, 0. So I'm going to start by plotting my key point just like always. Now I'm just going to follow my parent steps, and I've made some changes to them. Instead of going right, I'm going left because it's a reflection across the y-axis. I've got that negative here with my horizontal compression factor. So I'm going to go to the left a half and up 1. So that's my next point. I'm going to go to the left half of 4 is 2, so to the left 2 and up 2. Left 2, up 2. I'm going to go to the left half of 9, which is 4.5, and up 3. So 1, 2, 3, 4.5, and up 3. So this is my new function here. So I'm going to carefully do my best to connect the dots, and then I also want to label it. So that is the first one here. Now what's kind of nice is that this other one that I've been asked to graph has the same horizontal compression and a reflection across the y-axis. So that -2 is the same as this one. So these steps are going to stay the same, but on this question I have done a horizontal shift and a vertical shift, and look at that, I've also got a vertical compression. So vertical compression here means that I'm going to change these steps. So let's do those ones. So we'll write it up here. So this is a vertical compression by half. So since it's vertical, I'm going to change my up-down. So I'm going to multiply all those up-down steps by a half. Okay? So now I have my step pattern that's taken into account my vertical compression and my horizontal compression. So the next thing we need to do is figure out the new key point. So when I'm looking for the new key point, the first thing I need to notice is that we always need to factor out, if we can, what's underneath the square root. So when I write this again down here, I'm going to have y equals 1/2, and under my square root I can divide these both by -2. So I'm going to have -2 bracket x minus 2. I'm factoring out the negative. Close my square root, and then I'm going to have -3 at the end. So now I can read from my key point. So here is my horizontal shift. Normally we think -2 means that it goes to the left, but we know horizontal is the opposite. So our new key point is actually going to be +2. And then the vertical shift is down 3. That doesn't change at all. So here we go. 2, -3 is here. And then we're just going to count our new steps. So I'm going to go left. Remember, the left is because I still have that negative in front of my horizontal compression. So it's left 1/2 from my key point. So left 1/2, and then up 1/2. So it's going to be like smack dab in the middle of that box. Next I go left, half of 4 is 2, so left 2, and then up 1. Then I'm going to go left, half of 9 is 4.5, so I start at my key point, 1, 2, 3, 4.5, and then up half of 3, which is 1.5. So we can see that this one is much more compressed vertically. We just smoothly join our points the best that we can and label it. Luckily this is pretty close to there. Y equals 1/2 root of -2 x minus 2 minus 3. So this is how we're going to be graphing some functions. You need to practice this. It's easy to make mistakes and forget some of the steps of this, and it's easy to get your left right and your up down, all those things mixed up. So please make sure that you do a bunch of these practice and you use the Desmos graphing calculator to check your work. The last thing we're going to be talking about today is to recognize that horizontal stretches and compressions and vertical stretches and compressions are very much connected, and we can actually represent them as each other in many different cases. So many horizontal stretches can be written as a vertical stretch and vice versa. sometimes you're going to be given a graph and asked to provide the equation. So there might be two correct equations that you could provide, and that's fine. You have the choice if you would like to write something as a horizontal or vertical stretch. So let's give an example here with this reciprocal function. And so what we have is I've got this 1 over 3 and then 1 over x plus 1. So I'm just going to write this as two different things. I didn't actually change anything about this. I just pulled that 1/3 to the front. And in fact, this will give me the same graph either way. So let's check that on Desmos. So here I am in Desmos, and I have my first version here that was printed on the sheet. This red one, we can see that this is our reciprocal function, and we have 3 bracket x plus 1. So this has the vertical compression written as, the horizontal compression written, because it's with the x on the bottom of the fraction. On here, we've pulled that 1/3 out to the front. And if I turn this on, it actually is exactly the same function. The blue is right on top of the red. They mean the exact same thing. One is shown as a horizontal stretch and one is shown as a vertical stretch. So go on Desmos and check this for yourself. The next one we're going to look at is a parabola function. This is quadratic. And so right now we see that the 2 is inside of the brackets with the x. So this square applies to the 2 and the x. So this is a horizontal, it's going to be a horizontal 1/2, so a compression horizontally. But we can very easily represent this as a vertical stretch. Okay, so watch this. I take my square and I'm going to apply it to both. 2 squared, x squared, just using bed mass to get rid of my brackets. And then 2 squared is 4, x squared. So now all of a sudden the square doesn't apply to this coefficient. So this is a vertical shift now, a vertical stretch by a factor of 4. So this one is the horizontal because it is with the function. It's inside of the brackets. The square applies to the 2. So that's going to be actually a horizontal compression by 1/2. We've rewritten it, and this is in front of the function. It's in front of the x squared, so it's vertical, and it's actually a stretch by a factor of 4. Let's go back to Desmos and just prove that those are actually the exact same picture. So here we've got the red graph. We have 2x all squared. This is a horizontal compression by 1/2. And then we've got our horizontal compression by 1/2 means we're squishing it this way. And then we've got our vertical stretch by a factor of 4 as this blue graph. Okay, you can see that they're right on top of each other. They're in the same spot. So either we're compressing it by a factor of 1/2 or stretching it by a factor of 4. Those actually do the exact same thing to the picture of the graph. Let's look at how to do this with a square root function. Basically, this 9 is underneath the square root. It's a horizontal transformation. Let's make it vertical by pulling it out in front of the function. So y equals the root of 9 times the root of x. The root of 9 is 3. And now the root of x is inside the function. X is inside the root function. The 3 is in the front. So this is a vertical stretch by a factor of 3. This is a horizontal compression by a factor of 1/9. Those will give us the same graph in Desmos. Now I can do the same thing with this one, but please remember we always want to common factor out whatever we need. We always start there with these. So we're going to have 2x plus 3 all squared. And now in order to take this 2 out, right now it's inside the square applies to the 2, so this is horizontal. But I want to pull it to the front, so all I'm going to do is apply this square to the things inside of the bracket so I can get rid of the bracket. So y is equal to 2 squared and x plus 3 squared. And now it's very clear to see how we can get our vertical stretch by a factor of 4 compared to our horizontal compression by 1/2. And if you go through and you graph all of these, you'll see that they turn out to be the same picture. One thing that I want to show you is just how these relate to our function notation. So in our function notation, the square root, the reciprocal function, the square, those things are all part of the f at x notation. So we don't show those functions, we just show whether or not they're inside of it or outside of it. Inside means horizontal, outside means it's a vertical change. So let's look at this one for a second. This would be represented as f at 9x. It's inside of the function. So y equals f at 9x. If we change this one, we would represent it as 3 f at x. That's how we would change the notation. This represents horizontal, this represents vertical. Same thing up here. Here we would have y equals f at 3x plus 1. Okay. Down here we would represent it as y equals 1 over 3 f at x plus 1. Which one is horizontal, which one is vertical, right? This is a horizontal stretch or compression. This is the vertical stretch or compression. It's in front of the function. This one is inside. This is inside of the function, so this is a horizontal shift left or right. Over here, if we were to represent this function, we would have y equals f at 2x. We don't show the square because that's what the f part is for. That's showing that, hey, whatever function it is, in this case, it's a parabola, quadratic. We don't show that. But when we convert it to our vertical form, we would say y is equal to 4 f at x. Okay? So that's how we show the difference in our function notation. We'll do one last one. This one up here. Actually, we'll do this. So y is equal to f at 2x plus 3. And at the bottom, we say y is equal to 4f at x plus 3. So these actually represent the same change in the graph when our function is a square or is a quadratic function. Please let me know if you have any questions. There are practice sheets on the website for you to do. One of them is about horizontal changes, stretches, and compressions, and the other one is looking at graphs and telling me the equation. So please practice those. Let me know if you have any questions.